Welcome to EDU World Space.
Here in this problem, we have a cable that's suspended between 2 points that has a length of 100 feet. They tell us that the weight per unit length is 2 pounds per feet, and that the sag represented as the variable h is 12 feet. They want us to find the total length of the cable. For starters, our origin of coordinates are going to be directly at the center of the cable, where x is going to the right and y is going directly up. In order to solve this problem, we want to start by deriving the hyperbolic equation that defines the shape of the cable. And that equation is x equals the integral of ds over the square root of 1 plus 1 over f sub h squared times the integral of w as a function of s ds squared. Now, if we replace w of s with w and take the first integral, our x equation will become the integral of ds over the square root of 1 plus 1 over f sub h squared times w times s plus c1 squared. Now, the reason we have a c1, which in this case is a constant, is because we aren't evaluating any of these integrals using numerical values. So if we proceed to take the integral of this function using u substitution for the term underlined in red, u equals 1 over f sub h times w times s plus c1, where the derivative of that equals to w over f sub h times ds, and if we solve for ds, that equals to f sub h over w times du. Now, if we plug in all these variables into the original equation, we get that x equals the integral of f sub h over w, substituting in ds, over the square root of 1 plus u squared times du. Now, if you can remember, this integral takes on the form of an integral that's used for a trig function. In fact, the answer to this is the inverse of the hyperbolic sign of x over a plus c. So by simplifying our equation, x equals f sub h over w, we're pulling out the constant, times the inverse of the hyperbolic sign of 1 over f sub h times w times s plus c1, all in parentheses, plus c2. Since we have constants in our x function, we need to solve for those using boundary constraints. And those boundary constraints in this case will be s equals 0 when x equals 0 for the original equation. For dy over dx, that will also be 0 when x equals 0. Instead of focusing on the boundary constraints for the original equation, I want to focus on the second one. Because we have a function of x and not a function of y, we can't use our x equation above. But you have to remember that for this section, they gave us the equation that dy over dx equals 1 over f sub h times the integral of w as a function of s times ds. When you take the integral of that part of that equation, you get that dy over dx equals 1 over f sub h times w times s plus c1. And when you plug in dy over dx for 0, and you plug in 0 for s, c1 equals 0. Now, if you use this constant c1 as well as the boundary constraints for s and x and plug it into the original x equation, you'll get that 0 equals f sub h over w times the inverse of the hyperbolic sign of 1 over f sub h times w times 0, plugging in 0 for s, plus C1, which is 0, all in parentheses, plus C2, and you solve for C2, that equals to 0 as well, leaving us with a final equation of x equals f sub h over w times the inverse of the hyperbolic sine of w times s over f sub h. So instead of leaving x as a function of s, we want to solve for s as a function of s. So if you solve for x by first multiplying by w and dividing by f of h, the left-hand side will be w times x over f sub h equals the inverse hyperbolic sine of w times s over f sub h. And if you take the hyperbolic sine of each side and then multiply by f sub h and divide by w, s should equal f sub h over w times the hyperbolic sine of w times x all over f sub h. With this equation on hand, we're actually going to set this to the side for a moment because we know w, we know x, we're looking for s, but we don't know f of h. So we need to somehow find a way to solve for f of h. And the way that we're going to do this is by using this equation, where dy over dx equals 1 over f sub h times the integral of w as a function of s times ds. If you take the integral of that portion, dy over dx equals 1 over f sub h times w times s. And it would be plus c1, but because we have solved for that constant before, we know that it's going to be 0. So now that we have this formula, right, we have a variable s in here. And remember that we just solved for s. So if we plug in this function of s and substitute it in, we'll get that dy over dx equals 1 over f sub h times w times f sub h over w times the hyperbolic sine of w times x over f sub h. Now we can go ahead and cancel out like terms. W cancels out, f sub h cancels out, and we're left with dy over dx equaling the hyperbolic sine of w times x over f sub h. We're now going to take the integral of the left and right hand side of this equation, which will allow us to solve for y. And we do know what y is. At the beginning of the problem, they said that sag, which was represented by the variable h, was 12 feet. And because h and the y-axis run in the vertical direction, we can say that y equals h. Also, remember to put a dx at the end of this equation. So if we take the integral of this term inside of the hyperbolic sine using u substitution, we can say that u equals w times x over f sub h, where the derivative is equal to w over f sub h times dx. And if we solve for dx, that equals f sub h over w times du. And by substituting in these variables and solving for the integral for the entire equation, we get y equals f sub h over w times the hyperbolic cosine of w times x over f sub h plus c3. Since we have a constant in this equation, we need to solve for C3 by using the boundary constraints. And that would be y equals 0 when x equals 0. And by replacing 0 with y and 0 for x and solving for C3, that constant equals negative f sub h over w, which leaves us with the final equation of y equals f sub h over w times the hyperbolic cosine of w times x over f sub h minus f sub h over w. But if you want to simplify this further, it would be y equals f sub h over w times cosine, hyperbolic cosine of w times x over f sub h minus 1. If we use this equation to solve for f sub h, where we evaluate it when y equals h, which is the sag of the cable, which equals 12 feet, and where x equals half the length between the 2 points, which is 50 feet, and where w equals 2 pounds per feet, and we plug in these variables, our new equation becomes 12 feet equals f sub h over 2 pounds per feet times the hyperbolic cosine of 2 pounds per feet times 50 feet over f sub h minus 1. In order to solve this, I would not recommend that you do it by hand. I would implore you to use a graphing calculator where you plot the left and the right hand side and find where the lines intersect one another. If you're using a TI-83 or 84 graphing calculator and you want to know where to find the hyperbolic cosine, you need to hit the second button, catalog, which is directly above the 0, then hit the program button, which is where C is. It'll take you to the C section, and you'll scroll all the way down until you find the hyperbolic cosine. And when you find where those lines intersect one another, f sub h will come out to be 212.22 pounds. Now that we know what f sub h is, what w is, and what x is, we can go back to the equation that defined the cable of the shape, which was S equals f sub h over w times the hyperbolic sine of w times x over f sub h, and plug in all of our known values to solve for s. So if we plug in those values, our new equation would be 212.22 pounds over 2 pounds per feet times the hyperbolic sine of 2 pounds per feet times 50 feet all over 212.22 pounds, which gives us a value of 51.87 feet. But because we evaluated this from the origin to one end of the cable, this number is half the length of the cable, and they want the total length. So we have to multiply this by 2, which means that the total length of the cable, ST, is 103.7 feet, which is approximately 104 feet. And that is exactly how you solve this problem. I hope it helped.